Now this question is given in GATE 2005. What they are trying to ask is, if there are n processes P1, P2, so on Pn, share m identical resources, which means there is one resource and there are m instances of that resource type. M resource units which can be reserved and released one at a time. Okay, don't pay any attention to this. Reserved and released, it is not required. And now the maximum number resources required of a process Pi is Si, which means each process Pi requires Si units of the resource. So what they are trying to say is that there are m resources totally and n processes P1, P2, P3, so on Pn, and then they are saying that each process requires Pi requires Si units of the resource, which means P1 requires S1 units of resource, and P2 requires S2 units of resource, and P3 requires S3 units of resource, and Pn requires Sn units of resource. That is what they are saying. Okay, and now they are asking, the question is, which one of the following conditions ensure that there is no deadlock? That is what they are asking. So indirectly they are asking, what is the relationship between m, n and all these Si's so that there will be no deadlock. So in order to find it, you should find out what is the minimum number of resources required so that there will be no deadlock, right? And how did I ask you to solve it? Whenever such a question is given, you have to find out what is the maximum number of resources that can be present inside the system which will still cause a deadlock, right? And if you want to put the maximum number of so they are asking about the maximum number of resources, right? So when we are trying to solve this, what is the minimum number of resources which will lead to deadlock? We have to find out what is the maximum number of resources which will still lead to deadlock, isn't it? Now how can I solve it? If I have to solve this one, like saying what is the maximum number of resources which will lead to deadlock, then we should try to give the process as many resources as they could take but still be present in the deadlock. What do I mean by that is, give the process as many resources as it could take but still be present in the deadlock. If a process needs, let us say, n resources, give it n minus 1, that is the maximum amount of resources it could take, and still be in the deadlock. Why am I trying to do this? Because I want to find out what is the maximum number of resources all of them could absorb but still everyone could be present in the deadlock, isn't it? Therefore, in order to solve this, I am going to solve this one. What is the maximum number of resources m required so that there will be deadlock? That is what I wanted to solve. In order to do this, I will try to assign each process as many resources as possible so that they will take them and hold them and still be present in the deadlock. So I will assign P1 total resources of S1 minus 1. The reason is, if I give S1 completely, it will not be present in deadlock. Therefore, I am just holding one resource back. And P2 can be assigned S2 minus 1. This is the maximum it could absorb and still be present in the deadlock. And P3 can take S3 minus 1. So on, Pn can take Sn minus 1. So these are the maximum number of resources which each process can absorb, and then each process can take, and then they could be present in the deadlock. Then combinedly, what is the total number of resources that the system can take and still be present in deadlock? You have to add all of this. So if I add all of this, I could add if I put a plus in all of this, then addition, I could pull out all S1, S2, so on Sn, right? Therefore, what I get is sigma I equal to 1 to n Si, which is nothing but I am trying to add all the S minus n, that will be the sum. So even if I have these many resources, still the system can be present in the deadlock, right? Which means if the number of resources are less than or equal to this number, still the system can be present in the deadlock. If there has to be no deadlock, that is what they are asking, right? If there has to be no deadlock, then the number of resources should be greater than this. If the number of resources is less than or equal to this, deadlock is possible. If you don't want any deadlock, then the number of resources should be greater than this, which means this one, right? Then what happens? Then you can see the relationship. Then you can get that if you take this one and if you just do some reordering, then we get, is it visible? Sigma I equal to 1 to n Si, this one is less than m plus n. this is the condition we get. Okay, so this is how you can solve this. This is the option, right? Fine. So anyway, do one thing, don't by heart it, you please derive it. So people try to say this as formula and people try to by heart such formulas, but I really don't encourage doing any such thing. Please don't form any formulas. Generally what people do is, in competitive exams they'll try to create formulas, and by the end they'll create 100 problems, 100 formulas, and they'll all before the exam they'll try to mug them. I mean, they'll try to by heart them, and every formula is going to put lot of pressure on your brain, because you have to remember them, isn't it? And once you feel that you have forgot one formula, that is going to trigger a lot of tension in you, and that is really bad. So don't remember any formulas, try to derive it. It might take 1 or 2 extra minutes, but it is really worth deriving them instead of putting everything in your brain and putting a lot of pressure. Try to remember the concepts, which is very easy, and try to derive the formulas, don't by heart them. Okay, and one more thing is, even though the question looks so big and complex, the solution is very simple, as you found it out here, right? So in GATE, what my experience says is, if a question is very big, generally the answer is simple, and if the question is very small, it requires more intuition and thinking in order to solve it. Okay, so whenever you see any such big question, don't think that the answer will be difficult, and don't leave it. Okay, fine.